So, good afternoon, students. Today, we are going to take up our last topic from the biostatistics, and this topic is experimental design. So, whatever you have studied in biostatistics, this chapter entails and encompasses the methodology to apply that. So basically, this experimental design is an important tool in the hand of the investigator by which he can design his experiments in such a way so that he can find the true insights of the study. Basically, he will be able to overcome type 1 and type 2 errors in the statistical design, okay, and then he or she will be able to find out the causal factors for a response variable. So how to do that, we will be studying today, okay. So I think it can be covered in one session only, and if it calls for more sessions, then we will apply accordingly, okay. So let us start this experimental design, and in this we will be studying the, of course, the introduction about the experimental designs. Then we will be one of the major contributor in experimental design is again R.A. Fisher sir, and we will study some of the principles of designing experiments given by Fisher, and then we will be studying completely randomized design, and finally in your syllabus is randomized complete block design. So we will be completing up to this, although there are some more designs are there, but they can be studied if you are interested, and they will be covered when you will be taking PG courses, okay, after doing the undergraduation. So we will be restricting ourselves up to the RCBT, that is the, or we can say this completely randomized design and your randomized complete block design, okay. So let us start today's lecture. So basically, in its simplest form, an experiment aims at predicting the outcome. What it does? It predicts the outcome. Okay, and by introducing a chance of the preconditions. So there an investigator, what he does, he provides some preconditions in the experiment, and he want to predict the outcome, okay, which is represented by one or more independent variables, okay. So these preconditions, these are also known as one or more independent variables, and these are referred as input variables, right, okay. And also these are known as predictor variables, right. So basically the change in one or more independent variable is generally hypothesized to result in a change in one or more dependent variables. They are referred as output variables, right. So what we are saying here is that if we will be changing these input variables, so there will be change in the output variable, or in other language we can say that the output variable is dependent on the input variable. That is why output variables are known as dependent variable, whereas input variables are independent variables, okay. So the experimental design may also identify control variables, okay. So some are control variables that must be held constant to prevent external factors from affecting the results, okay. So control variables are those which can be termed as the external factors. Those can affect your results, right. So experimental design involves not only the selection of suitable independent, dependent and control variable, but planning the delivery of the experiment under statistically optimal condition given the constraints of available resources. So if somebody asks you the definition of experimental design, so this will constitute your meaning or the definition of the experimental design. So what a experimental design is, Experimental design involves not only the selection of the suitable independent, dependent and control variables, but planning the delivery of the experiment under statistical optimal conditions given the constraints of available resources. Now, experiments are much more effective than descriptive techniques in establishing the causal relationships. First, the unit to be studied are selected by the researcher. Okay, that is in experimental design, which unit will be constituted in your investigation will be selected by the researcher, and each unit is assigned to the group is also determined by the researcher. Okay, that is before commencing the study you will be having the liberty to select your units, okay, that on which units I am going to study that constitute the sample. Then each unit you can assign to a group, okay, in which you are going to give some treatment or preconditions, right? So the units do not select their groups, thus avoiding the self-selection bias. Then, second, in necessary consequence of the first, the researcher administered the predetermined treatment or treatments to the units within each group, right? So that is what I was saying, that to each group, it is the investigator which decides that the treatment will go to which group, right? Then, use of a control group is almost mandatory in experimental design. Okay, we can also have one control group, right? And what that control group will do? The control group, the inclusion of a control group permits a better isolation of the treatment component through a proper design like simple cross-sectional design. That is, in others there will be treatment in, but in one group we will not provide any treatment. So we can compare that when we have not provided any treatment. So this is the difference from the other groups. Okay, so that is your control, right? Now, a major contribution that the statistician have made to experimental design is the development of randomization concept. This is very important. Okay, what is randomization concept? That which enables the researcher to reduce the effect of uncontrollable variables. Okay, that is those variables which are not under the control of the investigator, those can be controlled using the randomization scheme on comparative measures of response to the variable that are under experimental control. So randomization is a useful device for ensuring on the average that uncontrolled variables do not favor one treatment versus the other. Okay. So by randomization, these uncontrollable variable will be divided equally among the treatments. Okay. So it is not like that one variable can favor one particular treatment versus. Okay. So in this lecture, we will be discussing two of the major experimental designs, which include completely randomized design, in short known as CRD, and randomized complete block design, that is known as RBD. Okay. So these two we will be discussing. So it may be mentioned that in the previous lecture we have given complete details regarding calculation of relevance, sum of square and app ratios for hypothesis testing. And I was telling you in the day before yesterday lecture that kindly go through the ANOVA before coming to this experimental design class. Okay. So we have tested the cases for one-way and two-way analysis of variance. Okay. So please go through the same for understanding the principles of breaking down the total variation into meaningful components of variation. Okay. And this methodology and principle remains the same in all the designs. And therefore, with a little more effort, you should be able to understand and work out the details. So it will be pertinent to go through Fisher's principles of designing experiment now before explaining CRD and RBD. Okay. So one thing is that you should have a basic background and the basic sound knowledge of the ANOVA, and then we should have some sound knowledge about the Fisher's principle of designing experiment before explaining the CRD. So what are these Fisher's principles of designing experiment? So in methodology of designing experiments was proposed by Ronald Fisher in his innovative book, and this book is being used by almost all the agricultural scientists. And this book has laid the foundation of ICAR actually in India. And this is the book on the principle of which all the agriculture universities worked for decades and brought about green revolution in India. So this is the all these varieties, breeds, anything which have been developed in India, those are based on the principles explained in this book. This principles of designing experiment. Okay. So the arrangement of field experiments. 1926 he has given one book, and then the design of experiments in 1935 was given. Right. So much of his pioneer work dealt with the agricultural application of statistical methods. Okay, and that is why his the things are being used as it is, and because of his work only we can say that we were able to develop such a, large number of varieties from the Mexican wheat we bought from other countries. Then we developed our own varieties, and that is why we have become self-sufficient in cereal production. Okay, particularly wheat. Once we were importer, now we are exporter. Okay, so as a mundane example, he described how to test the lady testing tea hypothesis, that a certain lady could distinguish by flavor alone whether the milk or the tea was first placed in the cup. Okay, so these methods have been broadly adopted in biological, psychological, and agricultural research, right? So he has given certain terms, and we should go through these terms before going for these experimental results. So one is comparison, right? What is that comparison? That in some field of study, it is not possible to have independent measurement with traceable metrology standard. So comparison between treatments are much more valuable than usually preferable, and often compared against a scientific control or a traditional treatment that act as a baseline. So particularly what we say that we have a particular traditional some values or scientific control value against which we compare our results. So that we can have an idea that whether our groups are significantly differing from those of the standards or not. Okay, say for example we can have a gold 22 carat, 23 carat, 24 carats. So accordingly we are producing something, we have a standard that this is 22, this is 23, this is 24, so we can compare them with the our production, right? So then comes your randomization. So random assignment is the process of assigning individuals at random to a group or to different groups in an experiment, right? So that each individual of the population has the same chance of becoming a participant in the study, right? So the random assignment of individuals to groups or conditions within a group distinguishes a rigorous true experiment from observational or quasi experiment. Sometimes you do not assign, you simply observe that this is happening, and based on say for example in this age group this is happening, this age group this is happening. So that makes your observational study or a quasi experiment. But when you yourself randomly assign the subjects to different groups or different treatments, then it is known as true experiment. Okay, so there is an extensive body of mathematical theory that explores the consequences of making the allocations of units or treatments by means of some random mechanism, such as tables of random numbers we have already explained in classes, or the use of randomization devices like playing cards or dices, etc. So assigning units to treatment at random tends to mitigate confounding, which makes effect due to factor other than treatment appear to results from the treatment. That is, whatever you are getting results, so uncontrollable variable will be hided. That is, they will be equally distributed among the treatments. So you will not be having any confusion, right? Now, the risk associated with random allocation, uh, uh, such as having a serious imbalance in the key characteristic between the treatment group and a control group. Okay, say for example, you are randomly assigning and you are studying for milk yield. So at the starting of the experiment, you may find that one group is having a higher milk yield and other may be having low. So that can be, these are calculable things. You can manage them. Okay, But what about those factors which you don't know? Thousands of inbuilt factors are there which are not under our control, and even we do not know them. So those has to be divided equally among the groups and without having any preference for a particular group. That can only be brought about through the process of randomization. Okay. However, if the population is divided into several subpopulations, that somehow differs, and the research require each subpopulation to be of equal in size, stratified sampling can be used. So other way to overcome this problem of having a imbalance is through stratified sampling that we have studied in our sampling chapter. Okay. So in that way, the units in each subpopulation are randomized, but not the whole sample. So the results of an experiment can be generalized reliably from the experimental units to a larger statistical population of units only if the experimental units are a random sample from the larger population. That is, you should have the experimental units chosen at random from the larger population. The probable error such as an extrapolation depends on the sample size among other things. So sample size is also another factor, right? So randomization is one of the essence of the experiment. Until unless you do that, you will not be able to have a check over the uncontrollable factors, right? Now comes your replication. What is replication? So measurements are usually subject to variation and measurement uncertainty. Thus, they are repeated and full experiments are replicated to help identify the sources of variation. To better estimate the true effects of treatment, to further strengthen the experiment's reliability and validity, and to add existing knowledge of the topic. That is why, because measurements are usually subjected to variation. So that is why we repeat them or replicate them. So, however, certain conditions must be met before replication of the experiment is commenced. The original research question has been published in a peer-reviewed journal or widely cited. The researcher is independent of the original experiment, and the researcher must first try to replicate the original finding using the original data. And the write-up should state that the study conducted is a replication study, and that try to follow the original study as strictly as possible. So this is how statistical replications of the studies can also be done. If somebody is claiming that I have developed a vaccine, okay, give me your experimental design, right? What are your preconditions? Then we will replicate the same thing in our lab, and let us find that whether the same type of results are obtaining. And when the same type of results are obtained, then the validity of those results will be strengthened. And if there is any lacuna or some paucity, that will be reflected in the results at some other place. So that is why statistical replications also play an important important factor in developing the results. Right now comes your blocking. What is blocking? So blocking is the non-random arrangement of experimental units into group. Concentrate on this word. This is non-random. Okay. Blocks consisting of units that are similar to one another. Okay. That is, in a block, all the units are as far as similar to one another. That is, they have very less differences among them, variation among them within one block. However, one block differs or vary from other block. So blocking reduces known but irrelevant sources of variation between units and thus allows greater precision in the estimation of source of variation under study. This blocking particularly we will be studying in detail that how it affects our results in case of randomized block. So you will understand that what is blocking, right? So now let us start our this lecture. The main theme, the first design, that is completely randomized design. Okay. So frequently an investigator wishes to compare three or more treatments in a single experiment. This is a most frequent situation that the investigator wishes to compare three or more treatments, okay, in single experiment. So in survey 2, he may wish to study several populations. For example, he may be interested in IQ scores from a standard test for students at 5 schools, or such comparisons could be accomplished by looking at the sample two at a time and comparing the means. Although feasible, there is an efficient method of comparison for more than two populations. And what is that? That is ANOVA, right? So one reason for the insufficiency of comparing two groups is that the standard deviation for the difference between two sample means is not calculated from all the samples, but instead uses samples only from the two population under immediate consideration. So this is the one thing. That is why it is important to use all the groups simultaneously to compare. Why F test is better than T test when we have more than three groups? Because when we are comparing two groups, so the pooled standard deviation will be from these two groups only. Whereas when we will be having F test, so pooled standard deviation or the variation will be from all the groups. So the variation of all the groups will be taken into consideration when comparing with each other. So it is always better to have all the groups side by side instead of having simply two groups, right? Then second, we feel intuitively that we shall almost find a significant difference between at least one of the pair of means. Okay, so the extreme ones, if we consider enough identical populations. So basically, when we have too many groups, so we increases the chances that at least some of the group may differ from each other. Okay, right. So that is why we go for this F test. So we can no longer now therefore instead of using two samples at a time, we wish to make a single test to find out whether the students from let us take an example, whether the students from 5 schools, okay, or from 5 population having the same population mean, right? So our null hypothesis will be that mu1 is equal to mu2 is equal to mu3 is equal to mu4 is equal to mu5. So this will be our null hypothesis. So we have 5 schools, okay. So mu1 is equal to mu2 is equal to mu3 is equal to mu4 is equal to mu5 is our null hypothesis, that at least all of these are equal, okay. And its alternate will be that at least one among them is not equal, okay. Two among them is at least two among them is not equal, okay. So our reason for making such a test is not that we think 5 population means may be equal, the probably are unequal. However, if a preliminary test fails to show that the means are unequal, we may feel that the differences are rather small and do not warrant further investigation. Okay. So in completely randomized design is primarily concerned with the test for a population means. So to study the means, it is necessary to analyze the variance. Okay. So let us consider one particular example. And what is that example? That example is that an investigator wishes to study the effect of fertilizer on the yield of the corn. Okay. So what he did, what is the difference between this ANOVA chapter and this chapter is that here we are assigning the units, we are assigning the groups, we are assigning the treatments. There, that work had already been done. It is observation, and from the observation we were doing ANOVA. But here, what he did, he is designing the experiment. So, investigator wishes to study the effect of fertilizer on the yield of the corn. So what he did, he divided the field into 24 rectangular plots of same size and shape. So he has 4 treatments. One is control, that is he give no fertilizer. In the second plot, series of plots, okay, he has 24. So there will be 6 plots in each group because he has 4 treatments, okay, out of which one is control, that in one simple field he applies he sow the corn and take the yield, so no fertilizer has been given in the first group, right? Then in the second group he provided this potash and nitrogen. Then in the third group, potash and phosphate. And in the fourth group, nitrogen and phosphate fertilizer. Right? So he assigned each treatment at random to the 6 of the 24 plots. So the yield in the bushels per acre are presented in the table given below. So what he did, he has 24 plots, okay, and of that 24 plots, randomly he assigned these 4 treatments, okay. So he do not know that which, say for example, I will just make this design, okay. Let this was his land, okay, and he was having 4 treatments, and right, so he made 6 by 4, right. So these were the plots, okay. So what he will do, that he will be randomly assigning the 4 treatments, okay. So say for example, he may have this these plot numbered 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 and okay. So what he will be doing is that he is having 1 to 24 number. Now he will assign random numbers, okay. So he will, from the table he will find that the random numbers coming are like this. Say for example, that first one is 21, then comes your 4, then comes your 12, then comes your 3, then comes your say for example 13, like this, okay. So the first 6 he will be then he will randomize the these 4 treatments, okay. 1 2 3 4, out of these 3 these 4 the 3 came first, okay, randomly. So he will assign this 21 this T3, this again T3, this again T3, this again T3, this again T3, and the next number is, say for example, is 8. Okay, so this will T3. Then next came your this 2 randomly, and your next random number was 20. So this T2 will go here. Okay, so this 21 here, this treatment 3 will be given. In 4 this treatment 3 will be given. In this 12 this treatment 3 will be given. Then in 3 this treatment 3 will be given. Then 13 also this treatment 3 will be given. And in 8th plot this treatment 3 will be given, okay. And then in 20th this T2 will be given, and so on. Okay, so basically what he did is he has applied the treatments randomly into the different plots, okay. And once he has applied, then these are the observations of the 6 plots. So the 6 plots for this T3 will be these one, okay, that is 21st, 4th, 12th, 3rd, 13th and 8th, okay. So these are the yields in the this third, right. So in this 21st plot he got an yield of 63. In this he got an yield of 57, right. Then in this 12th plot he got an yield of 81. Then in this third plot he got an this yield, that is 59, right. Then in this field he got an yield of 64, and this he got an yield of 72. So this is how these results are obtained. Okay. So this was the randomization scheme he has obtained, and this type of design is known as CRD. That is one way ANOVA. That is only treatments are there, and these are the replications or the observations he observed. Right. So what we will be doing? So here this Yij, sigma Yij is that these are the sum of these. So this will be the sum, and this will be Yi dot is that the mean of all these. Okay. So this will be equal to 72. So similarly, we will find the mean for all the treatments. And what will be your total sum? This will be 1896 and your overall mean is 70. Right? Now we will try to understand the your uh, here. Here we use the I to denote the number of treatment and J to refer the number of observations. The sample means are designated by y bar I dot, where the dot in the second subscript position indicates that we have arranged over the second subscript j. In other words, y I dot is the mean of all the observation in the ith sample. The overall mean is denoted by y dot dot, y bar dot dot. The two dots indicate that the mean is obtained by summing over both subscripts and then dividing by the total number. Okay. So, the investigator purpose is usually to learn something about the population from which the samples are drawn. To accomplish this, he needs an underlying model. Okay. So, now we will try to understand this model. Okay. This CRD. So, for this model, we assume that our 4 sample each consisting of 6 corneals are independent random samples from 4 populations. Okay. That is, these are 4 populations. Okay. So, and these are the samples from each population. This is one population, this is from one population, this is from one population. Okay. Now, the 4 population means may be designated as, so the mean of the sample is designated by y I bar dot. Okay, whereas that of the population from which it has been obtained, it is mu1, mu2 for second, mu3 for third and mu4 for fourth. Okay, these are the population from which these samples are obtained and these were the sample means we have obtained in this table. Okay, these are the sample means, not the population means. They have been obtained from the fourth population. This is from the third population, this is from second, this is from the first, right? So, we are assuming that the 4 population may be designated as mu1, mu2, mu3 and mu4. So, we arbitrarily divide each of these 4 means into 2 parts. The first part is the mean of the 4 population means, which we call the overall mean, and second part is the difference between the mean of each population and the overall mean. Okay, in symbols we can say that mu1 will be equal to mu plus alpha 1. Okay, and what this alpha 1 is? Alpha 1 is nothing but it is equal to mu 1 minus mu. So, if I will put here this mu plus mu 1 minus mu, so it will mu1 will be equal to mu1. So, this is correct mathematically. Okay, so this is the difference of the group mean minus overall population mean. Okay, so if you add all the alphas, so you will get that these will be equal to 0. Okay, so let us consider. So let us consider that the population mean from which these samples are obtained. Okay, although the sample mean is 72, it is 95, for third it is 66, but we are assuming that let their sample means be 70, 100, 70 and 80. We are supposing it. Okay, so the overall population mean will be 80. That is, you add all these 4s divided by 4, so it will be equal to 80. So therefore this alpha 1 will be equal to mu 1. What was mu 1? 70. And what is your population mean is 80. So it will be equal to minus 10, right? Similarly, alpha 2 will be 20, alpha 3 will be minus 10 and alpha 4 will be 0. If you add all these, so it will come out to be 0. That is minus 10 plus 20 minus 10. So these all will become 0. Okay. So the difference alpha I, this alpha I is equal to mu I minus mu overall mean. Okay, is often called the effect of particular treatment. It is called as effect of particular treatment, and it should not be confused with alpha, which is the probability of rejecting the null hypothesis. Okay, so In this particular example, this alpha I sums to be 0, and it is always the case. This alpha will be equal to 0. Now we think then that of the population mean as the sum of two parts. Okay, that is an overall mean, which is an average of the four population mean, maybe of little interest to us. Okay, and the part that we attribute to particular treatment. Using this notation, we can summarize the model just described by saying the observation Yij is an independent observation from a normally distributed population with mean mu and mu plus alpha I, and whose variance is denoted by sigma E square. Okay, so this Yij, basically you will more be understood this thing here. Okay, that is this Yij, this Yij, any unit in the above experiment. This Yij can be any of these, this 99 or this 82 or this 72 or this 57. We can calculate these values, okay, using this formula, right, where this Yij will be equal to mu plus alpha I plus there will be some error in the estimation which is known as epsilon I. Okay, so basically here we think that particular cone yield Yij is made up of the population mean plus alpha I plus whatever is left over, that is epsilon Ij. In our data, for example, if I take Y23, okay, that is Y23, what is Y23? Third, Y23 is equal to 82. This one, that is the, sorry, this second treatment, third observation. Okay, Y23, third column. This is 82. So this 82 can be written as is equal to overall mean, then the difference which came out to be 20, and what will be left? It will be minus 18. Therefore, if the mean yield of for the second population is 100, so epsilon, similarly this epsilon, this 2 3 will be equal to minus 18. So when you will add all these epsilons, so these will also count, will be equal to 0. Okay. So these 24 deviations from the random sample, 24 E epsilon Ij, all from a normal population with mean, 0 mean and variance sigma E square. So when you will be adding them up, this will be equal to 0. So in nutshell, what you should understand here is from this model, this is your model, final model. This is the your response variable, that is how much yield you are going to get in your plot. This will be your overall mean, which is not of the population, which is not going to change. Okay, this is going to change, this is constant. Now this is going to change, and it depends on the which treatment you are giving, this alpha I. Okay, and this error will be estimated based on the treatment the which you have introduced into your model. Okay, so in nutshell, if the effect of treatment is higher, if say for example this is estimated with these three values, this is constant, if this is higher, if this value is higher, so this will automatically will be lower Eij. Okay, so whatever cause we are telling, say for example here we were using fertilizer, if actually because of this alpha is higher, so the error in estimation of our yield will be lesser, so which will be reflected in our ANOVA. So this is very important, that is this is constant, this depends on these two values, and if we have selected such a factor that this value contributes higher, so error in the estimation of this value will be lower, and hence we have found a variable which is actually causing effect on the response variable, which can be estimated using the ANOVA. if it is not simply by chance that this is contributing the thing, we can say that this is having a significant effect on the estimation of y, and thus we can say that in our model our error of estimation of these values are reduced. Okay, so this is how this CRD model works. So when we will be developing this ANOVA, I am not discussing over here. So due to treatment, these are the degrees of freedom. Sum of square we have discussed in our previous lecture. So these are the mean square and these are the F value, and F value at the 5% is 3.10. So because this F value is greater than this table F value, okay, so we proceed finally, okay, since the F value exceeds the table value, we reject the null hypothesis and conclude that the four population means are not same and the treatment levels are different. That is when we apply the this your fertilizers, okay, so there is a significant difference in the yield, okay, that is this thing is affected by this thing, it is not mere by chance, okay. If this could have not been because of this alpha, this yij, then this thing will be go into error, that is this component, this residual component, this error part. So this will increase. If my treatment is good, so my mean square of the treatment, this alpha I will be increasing and this residual will be decreasing. Okay. And the ratio will increase. This is the basic concept of ANOVA and F table. Okay. And when this increase, so there are chances of significance and hence rejection of null hypothesis, and we can say that this Yij is significantly affected by alpha I. Okay, so this completes your CRD, and we will either can have break or we can just discuss this. So let us have some 15 minutes break, no problem. Okay, so we will again meet at 4 5, okay, to discuss our randomized block design. And that's all for this session. Thank you very much for your patience hearing. If you have any question, so you may ask in the next session, okay, as right now I am not having anything in the live chat box. So thank you very much for patience hearing, and we will again join at 4 5 to start our next session and discuss randomized complete block design. Thank you.